Oh, okay. This warm-up was inspired by an Instagram post last night from my friend Dan, who is a musician as well as a writer, and he actually told the story of his, he used to use tuning forks in order to actually tune his guitar. He didn't have an electrical tuner when he was a kid. So he had a couple of tuning forks, and he is kind of an experimental musician. He's done a lot of cool stuff using a lot of different sources of sound, and he has this whole like pedal board that he built, and I don't know, it's amazing. And so he started using the tuning forks to make sounds, and then one of them broke, and then he was like, well, I should get more because I want more pitches, and so he got a bunch more, but the problem was that they were aluminum, and they didn't work with the guitar pickup. So we had to figure out other ways of capturing that sound. So why is that? Yeah?
Well, I was thinking that aluminum doesn't, like, frequencies don't travel as well through aluminum.
Ooh, that's an interesting idea. I don't know if that's true, but that could be true. That's not the reason for this, but that could also certainly how sound travels through something. Like, I'm sure there's all kinds of mathematical stuff having to do with like composition of instruments and other things. Yeah, that's a really interesting point. Somebody else want to have thoughts? Ella, you have a thought?
I don't really know. I was just thinking about, like, this steel is carbon and iron,
Mm-hmm.
and then aluminum is just aluminum, so I guess steel is technically an ionic compound, even though it's like...
What's an alloy?
Yeah.
Yeah, we'll talk about that.
So, I remember, like, we were learning about, like, the properties of, like, metals and,
Mm-hmm.
so since they want to, like, use electrons, they kind of have, like, a puddle of electrons around them, and that's how they conduct electricity so well, so I was thinking maybe it does the opposite for sound.
That's also a really interesting thought. Yeah. Aluminum is also a metal, though, and it also, when it's just pure aluminum, is going to kind of bonds with the sea of delocalized electrons that you have so clearly remembered. What do you think, Finn? Uh-huh. Uh-huh. Mm-hmm. That is super interesting. We are going to talk about that. That is not quite the reason for this, but again, another thing that probably does play into a lot of material science regarding musical instruments and other stuff. So that would be fascinating to look into that aspect of it. Any other ideas? Differences between steel and aluminum that might cause this to work or not work? Yeah.
Maybe it's something to do with, like, the hardness, like steel is a lot of a sturdier substance, and I'm guessing it has lower vibrations.
Mm-hmm.
So then, like, sound waves might travel easier through a sturdier substance than something that's pliable.
Sure, that is entirely possible, but I don't know if that's true. I haven't looked at that, and that's not the reason for this. But I love the things that you guys are coming up with, though, these ideas about differences between the materials. And we are going to work backwards to bonding, and in that larger topic includes us kind of a little dabbling into material science. Anybody else have a thought who hasn't shared? So the way electric guitar pickups work, it's not like there's a little microphone there that's amplifying the sound and sending the sound itself to an amplifier, right? It's actually little magnetic coils. And the vibration of the strings disturbs the magnetic field, and that gets transmitted into sort of an electrical current, which then is what comes out of the amplifier once you've preamped it or whatever you're doing, depending on what kind of instrumentation you're using and what kind of effects. But that's the basics of an electric guitar, is that it's not the sound of the strings, it's in that sense, it's not directly the sound of the strings, it's the vibration changing the magnetic field. Steel is magnetic. Iron is magnetic. Aluminum is not. And so the vibration of aluminum is not as good at if you hit a tuning fork and bring it over to the pickups of your electric guitar, it's not going to be picked up very well because all you're getting is the sound vibration and not also the movement of this magnetic material that can interfere with the fields that the pickups are making. So I just thought that was super interesting, and it totally relates to what we're talking about today, which is transition metals. And this is our next section of the topic. There's a lot of cool stuff in here. It is all complicated, and we are just brushing the surface. So kind of like so much of what you learned in honors chemistry, you like relearned in this class or unlearned and learned that it was more complicated than that. We are at the very, very lowest level here of talking about transition metals and their properties. There's so much more, and every time I try to like read up on it before I teach it, it's like I know nothing. So I'm very much in the I don't know anything category here. But it's super interesting. But first, before we get into that specifically, into the transition metals, there's a section of this that I sort of skipped that was in the 1.3 packet. That's the one that I like tore out and I put in a different sheet. And it has to do with ionization energies. So we talked about sequential ionization energies of elements and of sort of the main group elements and how that can tell us something about the main energy levels in an atom, okay? And we're going to come back to this with the transition metals later today. But we also, in this 3.1 unit, looked at this, the trends in ionization energy across elements, and we talked about how there's a downward trend as we go down down a group, and there's an upward trend as we go across a period. But there's also these little blips where it's not following the trend that we're expecting, right? And you can actually see that on the P table as well. It sort of looks like there's a little greener area in the dark blue. So we're going to talk about what makes that happen first. So what's on this page one is basically what was on the page that I ripped out of the previous packet. But there's two different reasons for those blips. But it's the same basic idea, but there's two slightly different reasons. And it's important that you be able to explain them, okay? They love making you explain exceptions to rules and things like that. So if you think about the electron configurations, beryllium is going to have the full, both of them are going to have the full 1s orbital, right? And then beryllium is going to have, oops, sorry, I did that wrong. They're both going to have the full 1s orbital. And beryllium is also going to have a full 2p orbital, as is boron. And that's where beryllium, that's where we stop with beryllium. Boron adds another electron to the 2p orbitals, okay? The difference in energy of the p sublevel versus the s sublevel is relatively big, okay? It's certainly bigger than the like 4s3p, where they're almost exactly the same energy. And so it's the beryllium to boron, magnesium to aluminum transition is it's easier to pull an electron out of the higher energy further from the nucleus p orbitals than it is to pull it out of the s orbitals. So that's what accounts for that. the dip here is we've got one unpaired electron in the p, and it's easier to pull that electron out than it is to pull one out of the 2s. Yeah. That's a great question, and I think you'll see it's not very much higher than beryllium, and I don't know how to scale these sketches are, but I think if we look, let's go ahead and look on p-table. Sorry, I'll have to fix that later. Keep doing that. If we look, oops, I'm on the wrong tab. If we look at ionization energy, well, it is. It's about 200. Well, no, it's about 100 higher than beryllium, 100 kilojoules per mole. That's a smaller jump than between lithium and beryllium or between carbon and nitrogen. Or actually not between carbon and nitrogen. Oh yeah, no, because that's about 400, a little more than 300 kilojoules per mole difference from carbon to nitrogen, and only about 100 from beryllium to carbon. So I think the fact that it's so close to beryllium is because of this. The fact that it's still a little bit higher is because it has 2 extra protons that are pulling on those electrons. So, but yeah, that's a good point. I never really thought about how close the carbon was to the beryllium compared to the boron. I think it's just the extra electrons. And you see the same thing in the period below. So that's one of the reasons. And this is basically evidence of the existence of the sublevels. I mean, it's not the only evidence we have, but it's just like the successive ionization energies were evidence for the existence of the main energy levels. This is a little bit piece of evidence for existence of the sublevels. Later in the P block, we have another dip, and that has to do with removing a paired electron versus an unpaired electron. Okay, so if we look at this as our nitrogen, which you guys did a great job of drawing for the most part on your quiz. So if we look at nitrogen versus oxygen, oxygen has this one electron that is now paired. And if we remember that they don't want to be near each other, right? We can only fit 2 electrons in an orbital, and only if they have opposite spins. So kind of like, the siblings who don't get along sitting in the back of the car and just not talking to each other and looking the other way out the window because they don't want to be anywhere near each other. And first chance they get, they're going to get out of there. And so that's why this electron is easier to remove. Because of that repulsion that's coming from the other electron in the orbital, okay? Whereas the nitrogen electrons don't have that. So the nitrogen and then fluorine are going to follow that trend of more protons, higher energy, but we get this drop in oxygen because of that repulsion within the orbitals. Okay. And again, it's the same thing in the with phosphorus and sulfur, etc. So we'll come back to ionization energy in a minute, but let's talk about the transition elements. So we're going to go into a tiny bit of detail on a few of these, but just generally understanding some of these properties, that they exist, that there are ways in which transition metals have particular characteristics. That's not to say that they're the only ones that have these characteristics, but they just tend to be a little bit stronger in the transition metals. And in some cases, to the point where you wouldn't you wouldn't actually see that property, even if it's sort of there lingering under the surface in the other elements. So very conductive electrically and thermally. That has to do with the movement of the electrons. It's that when they are in a metallic bond, like Alice said, we have the sea of delocalized electrons. It's easy for them to kind of shift their position, and that also affects their the ability to conduct heat. The ability of the atoms to vibrate within the matrix of that metallic structure. Pretty high melting points, as opposed to a lot of the group 1, group 2 metals in particular. Malleable, that comes from mallet, same root word as mallet, which means we can hammer it into a particular shape. So it's specifically talking about hammering it, but really when we think about bending it, changing the shape of it, that's kind of the common view of what the word malleable means, and that also is true, tends to be true for these elements. And ductile is a duct, of course, is a long tube, and so if something is ductile, it can be pulled into a wire, basically. And then high tensile strength means it's hard to break it apart, relatively hard. So. And then magnetic properties, which we're going to talk about in slightly more detail. Chemical properties, you know already that they have different charges, and we talked very briefly about oxidation states at the end of last year, and we'll talk about that more when we get into redox. But unlike the group 1 and group 2 metals, they can show multiple charges, multiple oxidation states when they bond with other substances, and we'll talk a little bit more about that tomorrow. And the complex ions and colored compounds, that we are also going to talk about starting tomorrow. And I'm hoping to do a lab next week related to that. I did one last year that was kind of not super exciting, so I'm going to see if I can beef that up a little bit to make it a little bit more interesting. And then they can also act as catalysts, so like the gold and the palladium in your catalytic converter in your car. Nickel and iron both are used to catalyze the production of ammonia, the Haber process, and lots of other examples of this. So, and again, we're going to touch on that a little bit more a little bit later. So what is a transition element? We tend to equate D block with transition metal. And that's mostly true. But the IUPAC definition, the International Union of Professional and Applied Chemists, anyway, IUPAC, the group, the international group that makes a lot of definitions and sets naming standards and things like that, states that a transition element has to have an incomplete D sublevel, or its ions have incomplete D sublevels. And so, as usual, you're only responsible for the first row in the D block. And you'll see that if you look at the table of electron configurations of atoms and their ions, you'll see that copper can have a 3D10 in the, or has a 3D10 in the neutral state, sorry. But in an ionic form, it's 3D9 for a 2+ ion. And so all of these elements, either in the atom or the ion, have have room in their d orbitals, and the exception is zinc. Okay, so zinc has full 4s and 3d. And when it becomes an ion, of course, this was not as well answered on the quiz, it loses its s electrons first. Yo, question? Okay, loses its s electrons first, and so even in the form of an ion, which is always going to be a positive 2 ion for zinc, it still has the full d sublevel. So zinc is actually not considered a transition metal because it never has a incomplete d sublevel. What are you going to ask?
Yeah, why are those the ions formed?
Well, they are some of the ions formed. Okay? Yeah, there tend to be common ions formed. You'll see there's a bunch of +2s here. And there's a reason for that, which I think, I can't remember which slide it's on, but I shoved it a little bit earlier in the slideshow here. Like iron can make a +2 or a +3. Manganese can make a whole bunch of different ions. All of them can make a 2+, but depending on the element, they can make a variety of them. Which is why we use that Roman numeral for the naming of them, because we need to know which version we have, which ion or which oxidation state. Yes? I mean, it's in the D block because it is filling the electron that gets put there is filling the d orbitals. Okay, so it's the blocks are based on the atomic number, but also based on what orbitals are being filled, right? So it's being filled. It just but it's full. Like zinc is at the end, so it doesn't show many of the properties that the transition metals show, and we'll see that in the lab and in some other examples. Yes. We're going to talk about that. Yes. So, yes. So, magnetism. So, magnetism is actually a lot more complicated than this, okay? And this is one of those things where I look it up and I'm like, I want to tell them stuff a little bit deeper, and then I get into the weeds and I'm like, whoa, I really am not sure. Basically, almost everything is a little bit magnetic or a little bit paramagnetic or a little bit diamagnetic. But the extent of response to a magnetic field comes from how many unpaired electrons you have. And that's you'll notice these are all ions, so that can be in a bonding state as well as in a pure neutral state. Okay. So zinc doesn't have any unpaired electrons. And so it does not show an effect in the magnetic field. If you go deep enough into the weeds, there's always some response to a magnetic field. But when we talk about like putting a block of zinc in between two strong magnets so that there's a field in between, it's not going to really respond to that. Whereas a block of iron would absolutely, shift its position in response to that magnetic field. Question? Oh, I thought someone had a hand up. So essentially, the more d electrons, the more unpaired electrons in general you have, the more magnetic, the more you respond to a magnetic field. Okay, there's actually 3 different types of magnetism. What they're talking about here is paramagnetism. There's diamagnetism, which is when you actually have a bunch of paired electrons, and they actually are repelled by a magnetic field slightly. It's not a very strong effect, but it can be somewhat strong, and I'm going to show you that in just a minute. But the magnetism that we're talking about here is paramagnetic. There's also ferromagnetic, which is when it not only responds to a magnetic field, but that the alignment of the magnetic domains, the spin of the unpaired electrons, can persist after the magnetic field is withdrawn, which is how you like magnetize a nail, something like that isn't actually acting as a magnet itself, but if you treat it in a magnetic field, you can make that nail act as a magnet. That sort of thing. Yes?
Can I just clarify what I mean? Like, so, like when it had, like, sorry, since it has like all the electrons there, it isn't having much of an effect at all. But then if it has like a lot of electrons that it needs to be full, it would have like a stronger effect.
Yeah, it's not so much the spaces as it is how many unpaired ones do you have. Okay, because that is what allows the movement of the electrons to change slightly in a magnetic field. They're going to change if they're paired. Then the effects of the up and down spin kind of cancel each other out in the magnetic field, so you don't really see the effect. Both of the electrons are kind of being affected, and it also depends a little bit on whether we're talking about core electrons or valence electrons. Core electrons generally are paired, and you could argue that these are core electrons being added because they're in the third energy level and we already have a 4s. But yeah, in terms of the ions, there wouldn't be a 4s. Okay?
So the 3D level is full of unpaired
Uh-huh.
electrons that would be the strongest.
Yep.
Does it have to be 3D?
You mean, can it be 4D or 5D or something like that? Yes. It doesn't matter where you are on the table. In that, in terms of the effect of number of unpaired electrons on the magnetism. Okay. But there are some effects with having more paired core electrons, because all of those, as you start getting further down on the table, you have more sets of core electrons that are essentially diamagnetic because they're paired, and that's going to start swamping the effects of having the unpaired electrons in the outside or further outside. So there is still going to be an effect, relatively speaking, but it's not going to be as strong lower down, which is why so many of the things that use magnets are in that first row. Also because they're very available elements, though. And if you know about the super strong magnets you can buy, they are made with neodymium, which is down here in the lanthanides series. Lanthanides are often very magnetic as well. Again, because now you've got an F block where you've got a whole bunch of unpaired electrons. And so being able to sort of play around with that, having that space to like shift to having as many unpaired electrons as you can. And there's also the degenerate orbitals, as we'll see tomorrow. It gets more complicated than this. It's not, they're actually, under certain circumstances, we don't think of them as being all the same energy. So then there's also differences in that affect in substances and in elements, but also in compounds, depending on what the compound is, that can also have some small effects on that. So it's very complicated. This is the very simplistic version. Yeah. Yeah. Okay. And actually, I saw this on Facebook yesterday, and I was kind of excited to try it. So I have this little contraption here on this balance, and if you want to get up and come see it, I mean, what I'm looking at is just the numbers. But I've got some foam blocks. I've got a can that has some steel in it, and I've put 3 neodymium magnets on top of the can. So right now, this is perfectly balanced, and I've tared it to 0. Okay. If I take, which one is the one that worked well? If I take a substance that has iron in it, and I put it above there, it's not touching the balance, but what it's doing is it's pulling up slightly on the magnets. So it's making the numbers on the balance go negative. So we're down to 0.0237 with this jar of ferrous ammonium sulfate. Okay. And then if we have something, so something like, oh, I didn't bring the zinc out, but I do have some potassium. Here's some potassium nitrate. And absolutely nothing happens. Okay. I should try it with the zinc that we have. If anything happens, the numbers are actually going to go up because it's being repelled, because it's diamagnetic. It's more diamagnetic than it is paramagnetic. The most diamagnetic substance that we know of is bismuth. Here's some crushed up Pepto-Bismol tablets from a failed attempt at an IA. Let me just re-tear this. Oh my God, this worked so well. Just like, because it was in the process of tearing. Sorry, I jumped the gun. Okay, now we're back at 0. We put the bismuth on top, and we should start seeing an increase, meaning that it's actually pushing those magnets down. It's repelling the magnets, which is pushing down on the balance just a little bit. Magnetism is complicated, but we can talk about, in general, our transition metals. Here's some cobalt. Some cobalt chloride. You can see the numbers going down to negative 0.05. Cobalt being right in the middle of that, of the D block. So if you think about it, if you think about the periodic table and the electrons in these, the electron configurations of these elements, at the beginning of the D block, we have unpaired, more unpaired, even more unpaired, tons of unpaired, all the unpaired, and then we start pairing them up. So right in the middle here is where we're going to get the strongest effects, strongest paramagnetism. And then as we start filling up and pairing those electrons, the magnetism gets weaker and weaker. So until we get to zinc, which is not going to have a response at all. So anyway, that's my very brief demonstration. Although I will say this was in the IB Chemistry Teachers Facebook group, and somebody said, oh, that could maybe be an interesting IA in terms of coordination complexes and different ways of bonding some of these transition metals to use this setup to collect data. And I was like, that's interesting. That might be harder to do because I don't know how easy it would be to get a substance we would need. And also you'd have to have like a controlled area and moles of your substance in order to make sure that that was consistent across. But anyway, kind of fun. So for the purposes of this class and of the exam, more unpaired electrons equals more magnetic. Okay? Even though we know it's more complicated. Here is a table. I skipped to page 12. Here's a table showing some oxidation states. You can find these all over the internet, and they will have slightly different configurations. But what you'll see is that, again, as we get closer to the middle, where we have the most unpaired electrons, we have more options for our charge/oxidation state. So, manganese can have a bunch of different ion charges/oxidation states. Zinc can only have one. Almost everybody can have a +2 charge because that's losing their 2 4s electrons, right? And then not moving any of the d electrons. And then the more unpaired ones we have, and we'll talk about this a little bit more with the orbital splitting, the more options we have. So that's kind of the downward triangle of this kind of table. So it's also going to be related to magnetic strength. Yes?
How does manganese go up to 7 plus? Does more fat go into the lung?
I'm having a brain fart on the answer to that, but let me get to the next slide to talk a little bit about these the successive ionization energies. So this is basically what we're talking about, but not specifically manganese, and I feel like I should probably look into that. If this chart is comparing successive ionization energies for calcium and for chromium, and it's just it's easier to remove a variety of different numbers of electrons if you have a transition metal that has small differences between ionization energies. So it's relatively flat, as opposed to having the like flat-ish and jump, and then we have a longer flat period kind of for our transition metals. So I will get back to you on the manganese thing. Oh, you did?
Yeah.
Okay, good. Yeah, so we will talk more about the beauty of transition metals tomorrow.